time for a pop quiz.
I'm Mr. Meeseeks! Look at me!
Hardly even a practice test.
Why did you even rope me into this? Because he roped me into this! Well, him over there, he roped me into this! Well, he roped me into this!
Whatever lies beyond tomorrow is a little later on. Regardless of warning, the future doesn't scare me at all. Nothing's
Come on, Jeffrey, you can do it. Pave the way, put your back into it. Tell us why, show us how. Look at where you came from, look at you now.
Hello everybody, welcome on in. My name is Penn Center. We're here tonight for some machine learning. Hello Dexy, hello Sai. Hi Jeff, I feel like it's been a while, Jeff. How are you doing? We're waiting for about 20 more seconds until the ad break rolls through, and that way we get a full hour to ourselves without interruption. Hello over my, how you doing? Welcome in. We are back! Hope you're all doing well on this. It's frickin' dreary today. It's been raining and gross all day up here in British Columbia, but I am ready to do some machine learning. I was out of commission like most of August and most of September. It was pretty busy for me. I finally just started streaming again in October, but things are settling down a little bit, so after this coming week, we should be good for November, December. And maybe even into January. But yeah, August and September were wild for me. It was silly. It was just like, it was a lot of work stuff. Right, so like August was a lot of like making sure students were set up with their prerequisites, getting into the classes that they needed to get into. And a lot of September was, I'm working for the union right now as well, so there was a lot of stuff that had to get done over those last couple of months to get our website. They entrusted me to the website for some reason. They were like, "Oh, you're a math guy. You know how to use WordPress and design a website, right?" And I'm like, maybe." So, you know, like a month later, after ChatGPT and I had several beverages together, we finally have a functioning website now, which is great. No, I will not be hibernating. It doesn't get that cold where I am, so I will not be hibernating. If we get snow, I'll be quite surprised this winter, actually. Last winter was super mild. My greenhouse, I actually caulked my greenhouse, so I think that everything in the greenhouse will actually survive this winter. I will probably have kale for days. That's how not cold it gets here. Hey, welcome in, guys. Last time we were working on actually, let me open up Discord. And that way, for those of you that are new, I can potentially direct you to some resources. Also, ignore my... Oh, what the heck? Hello? What? Oh, there it is. Okay. Actually, I just got into James's server on an invite from Rex. Anyway, here is our October monthly schedule. So yes, I would have been on. We were on last night doing some A Link to the Past. So on Sundays, that's usually kind of my machine learning / Brian needs to learn Python day. And then after this coming week, things should get a little bit more leveled out. But for Spooky Week, we're going to be doing some more look outside stuff. But yeah, Sunday's kind of my designated math day right now. And for those of you that are potentially new, we have some resources in Discord. Hi, Famished. How's it going? Ew, Python stuff. Python is mandatory, isn't it? I don't know. People always tell me it's mandatory. So there's a link to the Discord server. And under the Machine Learning Forum, all of our resources are in here. So lots of resources in here and lots of just stuff happening in the general chat as well. So Sven and QK are doing a little bit of work in here, helping me out with some stuff as well. So we have been working through the Reese textbook, and we got into, where are we now? We did logistics, so I think we're in chapter 5? Yeah, chapter 5. So we're working with discriminant analysis. So LDA and QDA, quadratic and linear discriminant analysis, is what we are kind of working on right now. So we took a look at how, like, what that kind of looked like in the non-mathy way last time, and then we popped over and we started using, which text is this again? This is the hasty text. So we went over and started looking at some of the mathematical underpinnings here from the hasty text as well. That's not in linear regression, it's in classification. So we were looking at some of the computations for this discriminant analysis last time. And trying to remember what the fuck a covariance matrix was and all of the properties of covariance matrices. So that was last time. So I think today we're gonna start hopefully doing a little bit of coding. So I'm gonna actually just open up RStudio, because that's what this textbook uses. This textbook uses R. So let's get that fired up and ready to go. Rage bait at its best. You pick Java? Oh yeah, fair enough. I mean, I still, if you open up my browser, oops. Yes, I was getting lyrics from Rage Against the Machine. I still have my, like, you need to learn Python, and it's still, this has been open since like January, and I just haven't done it. I need to do it. I need to learn Python. I need to at least learn the basics. Hey, we actually started something. What's all this? I don't think I need any of that. That's the Titanic data set. Okay, well, I mean, this is the first thing that we need to do today, so let's open up these libraries. Okay, loading and exploring the wine data set. Wow, this textbook knows me. This textbook actually knows me. What is this wow about? Come on. We're raging against the machine learning today. And having a beer. So, loading and exploring the wine dataset. Yes, let's do it. In this section, you'll learn how to build and evaluate the performance of a linear and quadratic discriminant analysis model. Imagine that you're a detective in a murder mystery. Okay, how does this connect with wine? A local wine producer was poisoned at a dinner party when someone replaced the wine in the carafe with wine poisoned with arsenic. Damn, it's like what, season 4 of Attack on Titan. Someone just spiked the wine with spinal fluid. 3 other rival wine producers, are at the party and are your prime suspects. If you can trace the wine to one of those 3 vineyards, you'll find your murderer. Hot damn, this is kind of fun. Okay. As luck would have it, you have access to some previous chemical analyses of the wines from each of the vineyards, and you order an analysis of the poison carafe at the scene of the crime. Does anyone even, honestly, do people use carafes anymore? That feels so bougie to me. Your task is to build a model that will tell you which vineyard the wine with the arsenic came from, and therefore the guilty party. This is kind of fun. It's Mary. His wowiness is spreading. Wow. Do I have a wow? Do I have a wow sound effect? I don't think I have a wow sound effect. That's sad. Oh no. What? Future family. No, I don't think I do. That's super sad. I should have a wow sound effect. I should actually go on to Mary's stream and literally just record him saying, wow, and just like have that to like use later. I think that'd be pretty funny.
Did I jump scare you? Yeah, I bet I did.
I knew you were coming here for that, Famish. I knew you were coming here for that. Okay. Let's load the wine data built into HD class SIF package. After installing it, convert it to Tibble, and then export. Okay. So let's do this. I don't think I have this package. So this is the HD classification package. Boom. We're gonna pop in there, grab, I guess, the wine data set. Package equals HD. C is not. Okay, classification. Okay, looks like we're ready to go there. Let's grab error in find.package. Oh wait, there is no, what? Hello? Oh, I probably actually have to, wait, do I have to open up the library? Is that my problem? There is no, what? Did I spell it wrong? Oh, maybe such a package does not exist. Well, that's sad. Oh, there it is. Well, that's weird. Why didn't it work when I typed install packages? Oh well. I did not want to install the package. Have you guys been over on Mary's stream recently? How's Mary doing? I feel like I haven't seen him in a while. Okay, sweet. Let's load that up. Okay, hopefully we can now get the data. There it is. Okay, there's our wine stuff. And we're gonna make a wine tibble. Okay, so they said that the tibble is containing 178 cases and 14 variables of measurements made on various bottles of wine. We can take a little peek at what is in there. Okay, so we got V1 to V13. Yeah, and 178 entries. Okay. So it just says class. Okay, there are different classes, classifications. So I wonder if the class is from the vintner. Yeah, so there must be 3 different vintners or 3 different site locations. That makes sense to me. I have no idea what these variables are, though. They're just random numbers. And it just says V1 to V13. So they're just like 13 random variables that we have information on, and we don't know what they are. Okay, so this is what they were showing us. Or what I was looking at. Often as data scientists, we receive data that is messy or not well curated. In this case, the names of the variables are missing. Yeah, no shit. Okay, we could continue working with V1, V2, and so on, but it would be hard to keep track of which variable is which, so we're going to manually add the variable names. Wow, that's so much fun. Who said the life of a data scientist was glamorous? It's not. It's really boring. Then we'll convert the class variable to a factor. Okay, let's do some data cleaning. Okay, so data cleaning. So we're going to create a vector here with some different names. So I guess class. Oh, I see. Class. That must be alcohol content, I guess. Malic acid content. Ash. What's ash? Alkalinity. That's this one. Mag. Whenever I hear mag, I just think of the size of the bottle. I don't know what FE would be either. Something about phenolics? Flavonoids? Non-flavonoids. Pronouns? Color? Hue? What pronouns does our line have? Oh, there's more. Oh shit. Okay. OD. Yeah, we're gonna OD online. And prol. What would that be? I wish these would be more explicit. We could probably make these more explicit. But we'll follow along with the book for now. Okay, so they want wine to class. So this is changing the class. Wait, I need to actually do this. Oh, I spelt it wrong. I'm an idiot. Okay, that will relabel our top variables. This is going to change the class variable to a factor. Yeah, we want the class. Okay. So that's fine. I don't think we really need to look at stuff. It is important what kind of stuff pops out, so it looks like... I guess we can just open it up. I want to get rid of this, though, so I don't want to get confused with that. So let's remove that. And let's reopen this. Okay, that's fine. Looks like everything came out fine there. If we open it this way, does it give us that information at the top? Oh, it does, okay. So it looks like everything got labeled properly. We have factors, doubles, magnesium comes out as an integer. Everything else comes out as double, probably because of the decimals that are present here. Oh god, how do I... Hello? Oh no, did I go up too far? Oh no, did I lose my mute? Hello? Did I lose the thing? Oh, there we go. Why is it doing that? I have not. Oh, there we go. Okay, so I'm happy with all of that. That's fine. This is much better. We can see we have 13 continuous measurements made on 178 bottles. Fine, each measurement is the different amount of a different compound. Okay, don't care about his notes. You have only have 6 more chapters to read through in your programming course. And then you're going to be fully functional in Java, which is great. Yeah, pseudocode's fine and all. Like, it's good to get your brain thinking in pseudocode, because then you can kind of convert the pseudocode into various languages. But yeah, it's nice to actually take the pseudocode that you write down and actually try to put it somewhere, right? I've never programmed in Java, so I'm not super familiar with how easy or hard it is to do programming there. Now let's plot the data to get an idea of how the compounds vary between the vineyards. As for the Titanic data set, we're going to gather the data into and then tell you what? Why are we doing... What? Why do they talk about the Titanic data set? Huh? I think that's a spelling mistake. I think they mean to say similar to what we did to the Titanic data set in chapter 4. So we're going to use the factors, I guess, to plot all of these box plots. Can I just copy and paste this? Fantastic. Alright, and let's just make sure that we get everything looking roughly the way we want it to. Hello? Alright, that seems pretty reasonable. Okay, so there's our plot. Everything looks fine. So the box and whiskers of each continuous variable. For the box and whiskers, the thick horizontal line is... Yeah, okay, so I know on that. Suki range, blah, 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 blah. Okay. Really? I should be jumping for joy? I mean, things do look kind of different, I guess. There are definitely a lot of variables that show pretty strong differences, although there's a significant amount of overlap in some of these things. But hopefully there's enough differentiation that we... Right, like... There's always at least one class that feels a little different than the other ones. So in other words, I guess there's always at least two classes that feel very different from each other with regards to the boxes, right? Which is good. So maybe that's what they mean. Look how many obvious differences there are between lines. Yes, we should easily be able to build a well-performing classification model because the classes are very separable. And I'm assuming by separability they just mean there's, if we're looking at those IQRs, it feels like some of those IQRs are quite different, right? Like if I'm looking at, like alcohol content, right? I look at this second one, the IQR here is quite different than the IQR of class 1, right? Class 1 and class 2 are very different. Even class 2 and class 3 seem quite different, right? There's not a lot of overlap in the IQRs. So I think that's kind of what they mean. Like things, there's at least two that feel very, very different. And so if I can't use like the first variable to do the classification, then at least a subsequent variable should be able to help us do the classification. So let's define our task and learner and build a model as usual. This time we supply class of LDA, so linear discriminant analysis, as the argument to make learner to specify that we're going to use LDA. So they're saying LDA and QDA have no hyperparameters that we have to tune, which was the case for our regression stuff, right? Our logistic regression, I think, right? And we did something else. We did some kind of clustering before, didn't we? Was it a k-means or was it a KNN? I think it was a KNN. K-nearest neighbors had a hyperparameter too. Wow! Talk about a blast from the past. Not only do we have Jeff here, we have Enigma. Hello, Enigma. How are you doing? It's been a hot second. How's have you graduated yet, or are you still got the studies going? Okay, so in other words, all the information that LDA and QDA need is the data. Their performance is also unaffected by variables on different scales. They'll give the same result whether the data is scaled or not. So that means everything's going to get scaled through the process of using this algorithm. Okay, sweet. That's super helpful. All right, so we're going to create task and learner. Make a classification task. Our data is the wine tibble, and our target is the class variable. Right, because we want to be able to, based on the information that we're going to have coming in, we want to classify it as either 1, 2, or 3. Okay, that makes sense. Let's pop that in. Oh, wait. I keep spelling wine tibble incorrectly. Okay, so LD, I'm going to do capital letters here, just so I can find it. All right, make learner, and we're going to use the class if. Right, so we have our, let's make sure that things are looking good up here. This should be, yeah, our wine task, perfect, LDA model. Looks like everything's been built in here. So we have our list, our 3 lists. Awesome. 2 more years of machine learning and 1 more year of internship, including this year. Damn. 3 more years, hot dog. You were learning some crazy data type the last time we were talking. I think it was last night. You were talking about like bubble or something, bubble something. All right, let's extract the model information and get DF values for each case using the predict. What? What are we doing here? Okay, so there's something I need to refresh my memory on because it's been a couple weeks. So let's extract the model information, okay, and get DF values for each case using the predict function. By printing blah blah blah, we can see that the model has learned 2 DFs. These are, okay, what are these? These are this is the information that we need to make the line, isn't it? It's something weird, it's something like that. I'm just gonna scroll back and try to refresh my memory on what this means. We're just doing a linear right now. So we have data that looks like this, right? So we have data in like 13-dimensional space. So we are producing 2 DFs that should be like roughly 90 degrees to each other. I think they should actually be perpendicular to each other, right? And so we're basically trying to project this information into 2 dimensions using those 2 DFs. So that's what it's done for us. Okay, so it's doing the projection into 2 dimensions, and hopefully that projection gives us an easy way to cluster this data. So that's, okay, trying to refresh my memory, but I think that's roughly what they're trying to do here. All right, let's see, let's just kind of follow along and see what we get. So we're going to explore the DFs. This is our LDA model. Get a learner, a model, LDA model. What? Why do I have to do that? Oh, oh no, I just did something wrong. Whoopsies. Let's start over again. Okay. I did something bad. Okay, so let's get the learner model data. So this should be what?
Did I jump scare you? Yeah, I bet I did.
Yes, you did. You got me that time. Okay, this is going into the LDA model data. Happy Halloween, everyone. Which is this one. It's a list of 10. It's going into X. Stop it. No, this is something else. This is putting stuff into a function and then asking it to call X out. I guess I have to run this first. I'm just trying to figure out, like, usually this means go into column X and get some stuff. That's usually what this means. But so I guess I need, yeah, so I guess it's this, right? So I need to go into here. What? There is no column X. No, it's grabbing column X from this function. So it's not, I don't think I can easily find it. So it must be writing that information into this particular form for us. Although I'm a little confused. So, I mean, we get this. These are the coordinates, right? These are the X and Y coordinates that we get. And there should be 178 of them. Yeah, okay. So these are just our coordinates of the new information. Okay, so to visualize how well these two learned DFs separate the bottles of wine from the three vineyards, let's plot them against each other. We'll start by piping the wine tib data site into a mutate call where we create a new column for each of the DFs. We pipe this mutated tibble into a ggplot and call LD1, LD2 in class as the X, Y, and color aesthetics. Okay, finally we can add some dots. Okay, sounds fun. I actually want to type this out so that I can understand what they're doing here. So we're taking this data. This is the pipe command, so we're going to pipe this into the mutate command. Okay, so mutate. So the data we're going to work with is the wine tib data, that's fine. So LD1 equals LDA. What's this, Freds? Freds. Hi, Reese, how are you? Hello. Hello. One. Let's see if I can. LD2 equals LDA Freds 2. Okay, so that's going to go into, okay, so mutate's just adding stuff, right? Mutate is a way for us to take the data frame and add some stuff, like mutate adds stuff to the data frame. So, what's this comma 1 and comma 2? So, this is going into the predictor columns and adding the first column. Right, so LD, this would add the first column to the wine tib, and this will add the second column to the wine tib. Okay, so ggplot, aesthetics are going to be LD1, LD2, and color will be the class variable. That makes sense. Okay, and we're going to add to that G on point. That must be the ellipse around the clusters. I feel like we used this before, the stat ellipse. Theme black and white, I don't particularly care about, but let's see if this works. Okay, so the ellipse just gives us 95%. What did he say? Something about 95% confidence ellipses around each class. Okay. So here's what we get. It looks like it did a pretty good job. Like, we have very little overlap in our three colors. Seems pretty good to me. Now, can you see that LDA has reduced our 13 predictor variables into just 2 DFs that do an excellent job of separating the lines from each of the vineyards? Yes. Now let's use exactly the same procedure to build a QDA model. Okay, so this will give us a chance to see how these things are different from each other. I'm still not sure how we're going to use this information. So this is just the model with the existing data. We still haven't done any classification. But that's fine. Okay, so let's make a QDA model. Oh, it says, sadly, it isn't easy to extract the DFs from the implementation of QDA that MLR uses to plot them as we did for LDA. Sad. Okay, now let's cross-validate our LDA and QDA models together to estimate how they'll perform on new data. Okay, it looks like we'll do a k-fold cross-validation. What make resample disk? So we're going to do 2 cross-validations, one for the LDA, one for the QDA. That's why it has resampling. Yes, we're setting up the k-fold cross-val. And then, we're going to get 2 measures, the MMC and the accuracy. MMCE and the accuracy. Okay, so all this seems pretty similar to what we had done earlier. Oops. No, error unexpected. Unexpected comma. Where's my extra comma? Ah, here it is. Okay, I need a list there. Error in check measures, object MMCS. It should be MMCE. There we go. Now we wait. We wait for those 50 repeated tenfolds to work. Sweet. Okay. So what do we get here? Aggregated result. Why did we get 2 of these? Oh, one's the MMCE. and one's the accuracy. So super accurate. That's gross. 99%. That seems high. So let's see what our author says here. So learner equals our QDA. Everything else should probably be the same, right? Let's copy and paste this. Task resampling. Hello? Oh, sick. What happened here? Oh, I see. That's why it's not liking that. There we go. Okay, that worked. Okay, let's do the same here. And let's see if there's any commentary. Those feel really high to me, but yeah, here they are. So he gets it roughly the same. So about 0.2 and like 98%, 99%. They seem really high to me, but the QDA is definitely has a little bit of a higher accuracy, although they're both really high. Okay, you can create the confusion matrix if we want to. I'm just going to look at their information here. So what do we have here? So like if it's along the main diagonal, that means it was classified correctly, right? And anything that's off the main diagonal was not classified correctly. So yeah, so our error here pops into this bottom row. So 29 mislabels, 24 mislabels, and 51 mislabels. Is that 104? So I think the 104 is the sum of that row, right? So we had 104 mislabels plus 24 plus 51 is 104. Oh god. Okay. So what did these numbers mean again? So true. Oh, predicted is along the top. So let's see if I can figure out what this means again. So predicted, true. So 1, 2, so true. So everything along the left is what it is. And this is what the model said it was. So this 29 here means they were predicted as class 1, but they're actually class 2. This is interesting. So like look at this number 1. So this means that it predicted it to be class 2, but it was really class 1. That only happened once. So our biggest error is actually between classes 2 and 3. So we have 51 occurrences where we predicted class 3, but it was really class 2. Yeah, so class 2 gets incorrectly predicted quite often. Which is probably not surprising because class 2 like straddles the boundary of all of this information, right? If we go back to the box plots and we look at our box plots, I think that seems pretty reasonable, right? Like class 2 for the most part tends to straddle between these two classes, right? Like it's class 2 is often quite similar to one of the other classes. But classes 1 and 3 are usually quite different from each other. So how often do classes 1 and 3 get mislabeled? 0 times. So there are 0 times when it predicts class 3 when it should be class 1. Same down here, right? 0 times it predicted class 1 when it should be class 3. So class 1 and class 3 are not getting obfuscated, I guess. Okay, so that's kind of interesting. Now, detective, the chemical analysis of the poisoned wine is in. Let's use our QDA model to predict which vineyard it came from. Sweet. Poisoned. We're just gonna... Can I copy and paste this? Because this is annoying me. I'm just gonna copy and paste this. I don't want to type it up. I'm lazy. Okay, cool. so we have that information in. We're going to predict using our QDA model, and that means a capital M. New data equals poisoned. And this should be the output that we get? Is that what they're saying? It literally took I didn't even have to think about it. Oh, interesting. So it just says response 1. So it says based on the information that we have, it's most likely to be class 1. So the model predicts that the poison bottle came from Vineyard 1. Time to go make an arrest. Damn. Cool. I would imagine that if we predicted this using the LDA model, it would probably be the same. Oh, no way. Damn. LDA model says 2. Okay, well, I mean, that's interesting. So now we have an R script that will help us walk through LDA and or QDA if that feels like a reasonable approach to thinking about multi-dimensional data. So the idea here is taking the multi-dimensional data, trying to project that, in some sense, project it down into like a 2-dimensional space, right, where we're using kind of perpendicular pieces to create optimal clusters, right, to help us predict future data. Cool, so let's take just kind of a final look. I'm not sure exactly how far we go into 5. Yeah, okay, so let's finish off chapter 5 by just kind of reading 5.3, and I'm happy with that. While it often isn't easy to tell which algorithms will perform well for a given task, here are some strengths and weaknesses that will help you decide whether LDA and QDA will perform well for you. The strengths of LDA and QDA are as follows. They can reduce a high-dimensional feature space into a much more manageable number, right? They can be used for classification or as pre-processing, dimension reduction, technique for other classification algorithms that may perform better on the data set. QDA can learn curved decision boundaries, and LDA is linear decision boundaries. So, yeah, so it seems like the biggest benefit of these algorithms is to take multi-dimensional data and kind of dimension reduce it down to 2 usually. So the weakness of the LDA and QDA are they can only handle continuous predictors. Oh, that is actually really insightful to know, right? So it has to be continuous data. So we have to have the numerical data. It can't be it can't be what's the other kind of data again? So it has to be numerical. It can't be categorical data. Although recoding a categorical variable as numeric may help. They assume that the data is normally distributed across the predictors. Oh, okay, so that's also a pretty significant drawback, because not all data is normally distributed. We have to assume that. LDA can only learn linear decision boundaries. LDA assumes equal covariances of the classes, and performance will suffer if this isn't the case. Also assumes equal covariances. Interesting. QDA is more flexible, so can be more prone to overfitting. Cool. Interesting. Okay. So where do we want to go next time we get together? So that was classifying with naive Bayes. Oh, an SVM. Classifying with decision trees, and boosting. Random forest and boosting with decision trees. So I guess we do naive bays next. So I guess when we get together next time, we'll maybe start looking at support vector machines and naive bays. That seems maybe interesting. Although, like, when it comes to Bayes' theorem, I am definitely naive, is all I have to say. Maybe to end off the day, let's take a quick peek and see if there's anything interesting in the hasty text. So where did we actually get to? Here. Was it chapter 4 we were looking at? Yeah, reduced rank, regularize the scrim, linear regression of an indicator matrix. Maybe it was in here. Yeah, here it is. I think family might officially be over now, so we might have to end stream soon. But I want to do math. I want to do math. I want to figure out where I was. Where did we get to in the hasty book? Am I being too hasty? Physical components, squares. I thought it was in here. I thought it was 4.3, but maybe I'm wrong. Linear methods for classification. Oh no. Logistic regression. No, we didn't do that. Separating hyperpoint. No, we definitely didn't do that. I don't think we were in chapter 5. I think we were in chapter 4 somewhere. Nah, 24-hour stream confirmed. Not tonight. Maybe sometime in December we can do a longer stream. We were looking at some of this stuff. I remember reading some of these subtraction-y things. The class K observations. This is our covariant matrix. And then sigma hat was something else. Did we get to here? Oh no, we had gotten to here. That's right, we were working on this particular computation the last time, which I think we got relatively figured out in the Discord server. And there were some assumptions. So the assumptions come from the model that we're using, right? So the covariances being relatively the same, and then the normality of stuff, I think allows us to simplify this calculation, right? So we were looking at the log of the division of these two probabilities. Right, so it said, suppose that we model each class density as multivariate Gaussian, right? So that's our normality condition, right? And then linear discrete analysis arises in the special case when we assume that the classes have a common covariance matrix. So each of the sigma k's is sigma for any k that we want, right? So those were the two assumptions, and we were working on this calculation to see what happened. So in comparing the two classes k and l, it's sufficient to look at the log ratio. So yes, we did this last time. The equal covariance matrices cause the normalization factors to cancel, right? So we saw that a couple weeks ago, as well as the quadratic part in the exponents, which would be, it must be like these things. So this linear log odds function implies that the decision boundary between classes K and L is linear in X. Interesting. So that's why. So this is the setup, right? So this is the setup showing us why it becomes a linear kind of problem. In P dimensions, so it's linear in X, in P dimensions, a hyperplane. In P dimensions, a hyperplane. This is of course true for any pair of classes, so all the decision boundaries are linear. If we divide RP into regions that are classified as class 1, class 2, etc., these regions will be separated by hyperplanes. Figure 4.5 shows an idealized example with 3 classes and P equals 2. So the left panel shows 3 Gaussian distributions with the same covariance, but different means, right? So all of these covariances, look similar, right? But the means are all different, right? The pluses are all different. So included are the contours of constant density. Wait, included are the contours of constant density, enclosing 95% of the probability. Oh, I see. So these are the ellipses, the 95% ellipses. So the Bayes decision boundaries between each pair of classes are shown broken straight lines. And the Bayes decision boundaries separating all 3 classes are the thicker solid lines. What? The Bayes decision... Wait a second. The Bayes decision boundaries between each pair of classes is the dotted lines. Got it, okay. Right. Okay, so I think I can kind of see it. And then the Bayes decision boundaries separating all 3 classes are the thicker solid lines. Now, it almost looks like the thicker solid lines are just like a rotation of, or an extension of. It's actually just a 180-degree rotation of what we have, isn't it? It's a subset of the former. Okay. Okay, so here the data do arise from 3 Gaussian distributions with a common covariance matrix. Yes. Once we've included the figure of the 95% probability density as well as the class centroids, which are the plus signs. Notice that the decision boundaries are not the perpendicular bisectors. Okay, let's read this carefully. Notice that the decision boundaries are not the perpendicular bisectors of the line segments joining the centroids. Fine. This would be the case if the covariants were spherical and the class priors were equal. Okay? We see that the linear discriminant functions are equivalent descriptions of the decision rule. Hard max. In practice, we do not know the parameters of the Gaussian distributions and we'll need to estimate them using our training data. I'm getting a little over my head. Oh, the hats are the estimations, aren't they? I'm rolling with it. I have no idea how they would get the... There must be calculations that would show that these estimations make sense and maybe are non-biased. With 2 classes, there is a simple correspondence between linear discriminant analysis and classification by linear regression. The LDA rule classifies to class 2 if there's some kind of weighting decision made here, okay? And class 1 otherwise. it's getting a little bit above my head here, but with more than 2 classes, LDA is not the same as linear regression. Oh, they're saying if there are 2 classes, LDA might be the same as linear regression. That would probably make sense. Did they say that somewhere? So. Oh, here it is. With 2 classes, there is a simple correspondence between linear discriminant analysis and classification by linear regression. The LDA rule classifies to class 2 if blah, and class 1 otherwise. Okay. And then they're saying, with more than 2 classes, LDA is not the same as linear regression of the class indicator matrix, and it avoids the masking problems associated with that approach. A correspondence between regression and LDA can be established through the notion of optimal scoring, which is a different section. So getting back to the general discriminant problem, if the covariance matrices are not assumed to be equal, then the convenient cancellations in 4.9 don't work. In particular, the pieces quadratic and x remain. We then get a quadratic discriminant. Quadratic discriminant functions. I see. And the decision boundary between each pair of classes is described by a quadratic equation rather than a linear equation. So figure 4.6 shows an example where the 3 classes are Gaussian mixtures and the decision boundaries are approximated by quadratic equations of x. So page 103? What is that? That's like way back here. So the left plot shows some data from 3 classes with linear decision boundaries followed by linear discriminant analyses. The right plot shows quadratic decision boundaries. These were obtained by finding linear boundaries in the 5-dimensional space. Blah, blah, blah. Linear inequalities in this space are quadratic inequalities. Linear equalities in this space are quadratic inequalities in the original space. Oh. So x1, x2, the multiplication of x1 and x. Okay, so it's all possible combinations of x1 and x2 up to quadratic. Interesting. They're on like 111 or something like that. Oh yeah, here, it's here again, right? So 2 methods for fitting quadratic boundaries. The left plot shows the quadratic decision boundaries for the data at figure 4.1. Blah, blah. The right plot shows the quadratic decision boundaries found by QDA. The differences are small, as is usually the case. The differences look... they look a little different. Okay, well, let's read this last paragraph and then we're going to call it kind of quits here. Okay, so we had read up to... And here we illustrate 2 popular ways of fitting these quadratic boundaries. The right plot uses QDA, while the left plot uses LDA in the enlarged 5-dimensional space. I see. So, I mean, from my perspective, it's probably easier just to use QDA rather than deal with LDA in the enlarged space. But I think that it's interesting that's how it kind of works. The differences are generally small. QDA is the preferred approach anyway, which is cool. The estimates for QDA are similar to those for LDA, except that the separate covariance matrices must be estimated for each class. When P is large, this can mean dramatic increase in parameters, since the decision boundaries are functions of the parameters of the densities. Counting the number of parameters must be done with care. For LDA, it seems there are k minus 1 times p plus 1 parameters, since we only need the differences. Where k is some pre-chosen class. And each difference requires p plus 1 parameters. P plus 1 parameters. What are those parameters? It must have something to do with the estimations, right? Where are estimations for LDA? Did we do the estimations for LDA somewhere? I wish I had like an actual physical copy of this book. So that's that. No, it doesn't look like we did any estimations anyway. So these would be the estimations. We can estimate all of these. So we would need capital K, but we probably don't. No, this is fixed. N minus K. So why is it K minus 1? Why is it K minus 1? Because I guess we don't need to worry about the capital K. We don't need to worry about the actual class that we're working with, right? We just need to worry about all of the other classes, I think. I think that's the idea that I must be missing. Both LDA and QDA perform well on amazingly large and diverse set of class candidates. The question arises why LDA and QDA have such a good track record. The reason is not likely to be that the data are approximately Gaussian, and in addition for LDA that the covariances are approximately equal. More likely a reason is that the data can only support simple decision boundaries such as linear or quadratic, right? And the estimates provided via the Gaussian models are stable. This is a bias variance trade-off. We can put up with the bias of a linear decision boundary because it can be estimated with much lower variance than more exotic alternatives. This argument is less believable for QDA since it can have many parameters itself, although perhaps fewer than the non-parametric alternatives. I'm not sure my brain grew very much reading those couple of pieces, but that's okay. That's all right. That's all right. We do what we can. All right, folks. Thank you. This is great. Thank you very much for coming and hanging out. It was nice to see all of you, Famished, Enigma, Sai, Dexy, Jeff. Thanks so much. And Lobster. Oh my gosh. Thanks so much, all of you, for coming and hanging out. It was good to see all of you. I will be back for some more mathematics next Sunday. We'll come back and we'll keep on trucking through the next chapter of Reese, which will probably be another classification chapter. So maybe support vector machines, because I hear that term a lot and I have no idea what it means, and I would like to learn a little bit more about what that is. I feel like I have a rough idea, so the Reese textbook is nice as an introduction to these topics. I have a vague understanding of kind of when we might use LDA and QDA now, which is really nice, and I have a script that'll help me kind of guide through that process if I ever want to implement it, which is cool. The Hasty textbook is... I don't have a big background in stats, so it's a little bit over my head, but you know, I'm trying to piece together some of those pieces. If you want to add some flavor context, please feel free to do so in the Discord server. You're more than welcome to do Oh, Stuart, hi, buddy. It's good to see you. Oh, hey, how's it going? You came in right when I was ending. Yeah, so those of you that know a little bit more than myself, I mean, you're more than welcome to add some additional context that might be at a level that might be a bit more accessible. Because I do find the hasty text to be slightly, it's slightly over my head. And maybe that's because I just need to go back to the start and read it with a little bit more, less quick, like a more of an in-depth look. But I don't always have the time to be super in-depth with a really heavy statistics book like that. We'll get back there one day where I can actually like spend time reading and thinking about stuff, but that's not tonight. Which channel in the Discord? Oh, there should be a machine learning section, and you can post stuff in the general. You can post stuff under resources. So I know that Sven and QK have been posting some stuff in there. Just to kind of, help me read some more stuff and kind of, point me in the right direction on some stuff. So, the name of the book is I'm kind of predominantly working through 2 different textbooks. Both of them are in the machine learning section on the Discord server. So the main one we're working with is Machine Learning by Heffen Rees. And then the kind of more heavy statistics book that was suggested by individuals in... Actually, it might have been... No, I don't think it was you, Stuart. But somebody in the channel suggested the Hasty book. So it's The Elements of Statistical Learning by Hasty. So there's Reese. This is Machine Learning... Basically, if you look up that one, you'll be able to find... That one has, like, R and the MLR package and stuff like that. And then there's Hasty and others, and it's called The Elements of Statistical Learning. And so that one, I would say, is probably... Reese is the introductory book, which is what I'm kind of reading and trying to do a little bit of my introductory reading with. And then the Hasty book tends to be... at a bit more of a level for those of you with a statistical background. So if you've taken it's been a long time since I've taken statistics, so mathematical statistics. I can do the basic stuff. I can do basic, inference and basic probability, but I haven't really made it into the advanced statistics world quite yet. So the Hasty textbook is slightly over my head just because it's multi-dimensional. And I have to be really careful with some of those computations. But yeah, if you want to add some connotation or extra stuff into the Discord server, you're more than welcome to. If you can't find those channels, just let me know. It's probably just because you need a special tag or something. You may have to go to the top of Discord and actually say like, yeah, I want to be a part of the online classes. I think the online classes tag will get you into the machine learning section of the server. So we're gonna go ahead. It doesn't look like we have any of our typical friends on, but it looks like High Potential is on. So we'll go ahead. We'll raid over into Tinker. Maybe it was you, Pui, then, that was saying Hasty. Yeah, like I know people have recommended and said like it's a good textbook. So I'm happy that I have it in my collection. And maybe one day we'll actually do a very thorough read of it and try to work on some of the examples that they gave. When am I back next? So I'll be back on Wednesday evening. We're doing spooky streaming. We're doing some more gaming streams this week. So we'll do a spooky stream on Wednesday night, and then we're going to be playing Zelda with Dexy and friends on Thursday night, and then back with some more machine learning / Python learning next Sunday after I'm done work at the brewery. So until then, take care, everyone. We will have a little raid message here if you want to pop a raid message in for Tinker, and we will talk to you guys later. Goodbye, everybody.